So I'm going to try to wrap up everything we've talked about so far, which is sort of an impossible task, even accounting for the fact that we plan to go on and talk about further things next quarter, because the whole issue of understanding Hecke operators turned out to be more interesting than I thought it was when I started out trying to describe this so-called fundamental theorem of Hecke operators. And so that led us into some complications, which are very nice complications, but take a while to really explain. And we've been trying to do that, and I want to try to wrap it up in some sense now, but it's going to just be a kind of partial wrap up. And then what I want to do is talk a tiny bit about what I might want to talk about next quarter. So, okay, so we've outlined a certain theorem. This theorem is not really the fundamental theorem of Hecke operators. It's, in a way, an even more important theorem on which that result about Hecke operators relies. And it goes like this. So there is a category, I'll call C, which has finite groupoids as objects, and spans of finite groupoids as morphisms. Now we have to be a little careful about that, because when you compose spans, the composition is only associated up to some equivalence relation, which I'll explain. And so really we get a two category, but I want to keep things simple, so I'll just work with equivalence classes of spans, which I will describe a bit more later. Equivalence classes of spans of finite groupoids. And so I need to say more about that category, but marching right ahead, there's a functor, which is a kind of decategorification process that we've been talking about, which goes from that category C to the category of finite-dimensional vector spaces and linear operators.
I'm sorry, can you say what do you say finite groupoids?
No, finite groupoids.
Spans of finite.
Oh, okay. Sorry. Yeah. Thanks. So there's a functor from here to here, where these are finite-dimensional vector spaces. We often just work over the complex numbers, but today, just to show off how we work over an arbitrary field of characteristics 0. We saw that some of our formulas involve dividing by integers, so we want to be able to divide by any integer, so let's take that to be k to be any field of characteristics 0. Physicists out there in the audience, field of characteristics 0 means a complex number. C, R, rational numbers. Okay. Field where you can divide by anything. So how does this go, roughly? So I will just say a little bit about it, and then I'll sketch a tiny bit more later, but to get going here, just so you know what the heck I'm talking about. Nothing new. It's this. So it takes any groupoid and turns it into a vector space. Any finite groupoid, let's say, and turns it into a vector space, which is just what we're calling the homology of the groupoid, which, remember, is just the linear combinations of isomorphism classes of objects in the groupoid. And then it'll take a span of finite groupoids, and so these are all three finite groupoids here, and turn it into a linear operator from the homology of the first one, x, to the homology of the second one, y, second leg of the span. And the way it does it is by this pull-push method, meaning that we know that homology is a covariant functor, so we can certainly go forwards along the downwards arrow. Let me give these arrows names. Let me call them P and Q. So we can push forwards from the homology of x to the homology of x using Q, homology of y using Q. But then there's a trickier method of going backwards called transfer, and we use that to go from the homology of x up to the homology of x. So this arrow down here is just defined to be the composite of these two, and that's what our functor gives us, this arrow here. So we've talked about that. And there are all sorts of subtleties and caveats and issues, but everything I said is true, but there's a lot of subtleties involved. And let me just mention a couple of them. So that's the statement of the theorem so far, but this is sort of some critical apparatus, extra stuff that you may need to know to understand what we're talking about. So, for example, when I say there's a category where the morphisms are these equivalent classes of spans, you want to know, okay, what is this equivalence relation, and how are we going to compose spans? So we say, I've answered the first question for sure. So we say two spans are equivalent. Two spans from x to y are equivalent if the following thing happens. So we have this one span S going from x to y. We have another one, S prime, going from x to y. And I've written this before. There's a sort of obvious notion of equivalence, which is you want an equivalence of groupoids going from S to S prime. So that's a functor between groupoids that has an inverse up to natural isomorphism. Making this diagram commute, and I guess, again, we really probably should say up to natural isomorphism. So this, so if we have commuting up to natural isomorphism. So the point is, that's just the relevant notion for two spans to count as the same, and some point or other we would have to check that if you have two spans that are equivalent, they're going to give you the same linear operator when you apply this functor d, so that this functor d is really well defined. So equivalent spans give equal operators. So these are things that we haven't checked. But are pretty easy to check if you grind your way through it. So that's one thing. And then another thing is, how do we compose spans? Oh, now everyone's invited to the party. The whole world is how do you compose spans? We're trying to get a category where the morphisms are these equivalent classes of spans, so we have to know how to compose them. So we compose spans of groupoids the weak pullback, the point is that we've already talked about composing spans of sets, and this is a lot like that. But it's categorified one notch, so it gets to be a little bit subtler. So say we have a span of groupoids from X to Y and another one from Y to Z. So the idea is we would form a new span all the way from X to Z, which I'll just call S prime perhaps, or maybe S prime S if you like to turn things around when you write the composition. And that would be a new span of groupoids, so it's really a span all the way from X to Z. And it's formed as a kind of pullback of this portion of the diagram here, this part of the square. We write a little dynasty thing to mean pullback sometimes, if you want to convince people you're really a category theorist, that's a pullback. But this is a weak pullback, so maybe it should be sort of maybe a little more fuzzy or something. But what is it? What is it? That's the real question. So I guess I need to give names to some things here, so let's call this first span, we'll call the functors in it P and Q, call this other one P prime and Q prime. So remember, this is a span of sets. The way the pullback works is that an element of this set would be an element of this set together with an element of this set that both map to the same element down here. But we're not doing sets anymore, we're doing groupoids. So we have to ask what's an object of this groupoid SS prime. It's an object of SS prime. So it will be very similar. It's an object, let's say little s of our groupoid S, and an object little s prime of our groupoid S prime. But now we don't want to say that they get mapped to the same thing in Y. We want to say that they get mapped to an isomorphic thing. And we really want to say isomorphic via specified isomorphism. That's the yoga of categorification. So we say this, and an isomorphism, say alpha, going from Q of S to E prime of S prime. So that's what an object is. Now we really need to actually calculate some composites of spans of groupoids to give any sense of why this is such a nice thing. Now I guess I'm probably not going to do that today. We're building up all this technology, and we're just like barely building it up in time for the next quarter when we'll use it. But when we actually start calculating these things, we'll see. It's very sensible notions, very geometrical, nice notions. But I just want to charge ahead. So in addition to saying what the objects of this groupoid are, I can say what a morphism is. So a morphism, something going between two objects. So let's write down two objects and figure out a sensible notion of morphism. Here it's possible I'll make a mistake, so Jim has to catch me when I do. So a morphism in this weak pullback is, okay, so I'll write down one object, which I already did over there. Alpha goes from P of S, Q of S, T prime of S prime. There's one object. Let me call that object number 1. So let me put a 1. Okay. And then I'll have another object. In fact, let me write the alpha 1 here. So I have another object, so the same kind of thing, but with a 2 everywhere. And we're just trying to figure out what a morphism between two of these things should be.
Want it to be a groupoid.
If we want it to be a groupoid, it'll sort of almost have to be a groupoid because it's built out of stuff that are groupoid. So So we're going to try to somehow go from here to here, but whatever stuff we stick in here is almost bound to be invertible because all we have around are groupoids. So what do you think it should roughly look like?
It should be it's got to come from a morphism from S1 to S2 and a morphism from S1 prime to S2 prime that are hit by our Q and T.
That's certainly a darn good guess. So it should look like a square. That's the obvious way to go from an arrow to another arrow. So it's a square. And then you have two choices, which some of you may remember. We could either just stick any old morphism down in wherever it is, in Y down here, or you could stick Q of some morphism up above, which somehow is appealingly symmetrical. That we're doing similar things with morphisms to the object. Again, if you look at some examples, you'll soon see what's really right.
Are you saying it doesn't matter?
No, it does matter. It makes a big difference whether I wrote Q of F, where F was a morphism up in S, versus just a morphism down in Y. Because there could be a lot of morphisms in Y that weren't of the form Q of F. And also, Q might be very non-one-to-one.
But this is the right choice then?
I think so.
Yeah, it's the right one. I wouldn't be at all hesitant saying that, except that just the other day I was doing some calculation where something similar was going on, and I got surprised and something didn't work the way I thought.
I thought you were going to, is this Q of F, that's an isomorphism then, right?
Yeah, here everything is an isomorphism because everything inside is a groupoid. Now you might someday be dealing with weak pullbacks of categories instead of groupoids.
I thought you were going to say there was a different choice. It seems like you could pick QF and then the other side would be uniquely determined. Or you could pick P prime, F prime, and then QF, just by going around the square.
Yeah, I guess that's yet another choice, a third choice. You pick this one, that forces this one to be what it is. That would be another wrong definition.
It forces, if you pick Q of F, it forces...
Because everything's invertible.
No. But it forces the last one to be P prime or something.
No, it doesn't
Yeah,
force that.
that's the thing.
Well,
That's right.
So this is more...
And even if it does force it to be P prime or something, we don't know what P prime really needs to be. So anyway, there are lots of slight variants. And again, thinking about examples, which we will definitely do next quarter, will let us see what's a sensible thing and what's not.
And we don't want sort of equivalent classes of these things.
No, we're not.
On
So yeah, that's right. So what I've done here is I've got groupoids, spans. I've told you how to compose spans, and then you might hope that composition of spans is associative, since you're trying to get a category. But it won't be associative. It's just associative up to equivalence, and that's why I'm putting in this equivalence relation. So this composition is associative, and it has units. They're identity morphisms up to equivalence. Precisely that equivalence relation that I've described. So now that's a sort of lowbrow approach, although this may seem like painfully abstract already. This is a lowbrow approach, because in the highbrow approach to math, you never have equivalence relations unless you're like forced to at gunpoint. So the highbrow approach is that we think about a two-category with groupoids, spans, and things going between spans, which would be these equivalences, and then we'd be getting a weak two-category. But here I just want to get a category that I'm calling C, and so I'm going to need the composition to be associative, so I have to modify this equivalence relation. Okay, so that's sort of perhaps enough data for the statement of the theorem to actually be precisely defined. At least if you go back and look at James' previous lecture for the definition of the transfer, right? So I won't remind you of that formula for transfer, but that's something we also are supposed to So I'm hoping that somebody like Christopher will fill in the details and prove this theorem. So I'm not going to try to do it right now, because I just don't want to end off the class proving a theorem. It's not really, shouldn't be grungy, but there's a lot of more fun things to do. For example, stating that darn fundamental theorem of Hecke operators, that all this stuff is supposed to be a prerequisite for. So using this functor that we've got, going from category of groupoids, spans, groupoids and equivalent classes of spans, to finite-dimensional vector spaces, we can do this piggybacking maneuver that Jim mentioned. We can turn a category, say A, that's enriched over C, and turn it. Where is that term? You can turn a category enriched over C into a category which I'll call D bar of A. I think that may have been the terminology in the piggybacking method. Enriched over finite-dimensional vector spaces. So the idea of this piggybacking, remember, is that a lot of times, instead of the category just having a set of morphisms from some object to another, it has something a little bit more interesting, like a vector space of morphisms from one to the other. Or even a groupoid of morphisms from one to the other. And when you're in that type of situation, you say, we don't just have a mere category, we have an enriched category, a category that's enriched over vector spaces or groupoids or whatever. And so here, we are considering a category enriched over C, so the sets would actually be groupoids, and we're turning it into a category enriched over finite-dimensional vector spaces, and that means that the Hom sets are actually vector spaces, finite-dimensional vector spaces. So, roughly speaking, the way it starts going is that if you look at the morphisms in D bar of A from some object to some other object, that Hom thingy is going to be obtained by doing D to the Hom thingy in A from and so on. So the idea is that D bar of A has the same objects. I should have said that first. D bar of A has the same objects as A. Only the Hom thingies are different. And the reason why I'm saying Hom thingies instead of what you might normally expect as Hom sets is because in fact that's variable. A was a category enriched over C, so the Hom thingies were objects in C, i.e. groupoids. And then we're turning them into vector spaces over here.
I don't know anything about this enriched category. Does an enriched category always come with a two-category structure coming from the category structure of C?
No. The way you get the definition of an enriched category, which we've been careful to avoid, is if you take the definition of a category that goes like this: set of objects, let's see, the class of objects. And for every pair of objects, there's a set on X1. And you cross out the word set right there, and you say object in C. And then you go on and you say, and in the definition of category, you say there's a composition function, and instead of function, you cross that out and you write morphism in C. And that composition,
So C should have some tensor.
so C needs to have a kind of product, right? Because the composition goes from hom x, y times hom y, z to hom x, z. That's the Cartesian product of sets when you're working with plain old categories. We need to cross that out too, or draw a little circle around it, call it a tensor product. So you need to have some kind of notion of a product of objects. But in your C, you can talk about enriched categories.
Hom x, y is an object in the category C, right?
Yeah, that's right. So the idea is, you take the definition of category, and wherever you saw a hom set, you say hom thingy, where thingy means object in C. And then you just fix the rest of the definition so that it makes sense with that change.
But you will not talk of morphisms in C. Become two morphisms or natural forms.
No, you don't always get a two category. Enriched category is not necessarily a two category. There's one famous case where it is, which is when the thing you're enriching over is something like cat. So then your hom thingy is with the hom category. And so you could talk about objects in there, but also morphisms between.
Oh, so what happens to the morphisms in all of the other cases? You just said.
Well, the morphisms are important in every case. So the morphisms show up because, remember, in an ordinary category, composition is a function between hom sets, product of hom sets. When we enrich, it becomes a morphism in C from this object in C to that object. So the morphisms show up, and C also requires a tensor product. So the technical thing that we've been avoiding saying is that, in general, to enrich over C, C needs to be a monoidal category, a category with a tensor product. Then you can define the concept of it.
So you're saying you need a product for the object of C, the piece of thing you're enriching over?
Yeah, because let me just sort of say, let me illustrate this by saying a little bit more about what a category enriched over C for our particular example amounts to, and then maybe some of these things will seem clear. Yeah?
I was just saying, if you just look at the invertible morphism as the isomorphism, does that lead to something like
Isomorphisms where?
in
Sorry.
C? In C. I mean, so far in the definition of this category, morphisms in C do not play any role.
Sure. It plays a role in the composition is a morphism in C. Let me do an example.
Oh, okay.
So for us, right, C is groupoids, equivalence classes of span, finite groupoids, equivalence classes of span. So let's think about what a category enriched over C would be like. So a category, and it's good that we're going to think about what it's like because we're going to do an example. And the point of all this abstract analysis is to consider the example. It's the fundamental theorem of Hecke. So a category enriched over C has a class of objects. I'm calling it a class now just to point out that when we're going from ordinary categories to enriched categories, we're not messing with the fact that you have a set or class of objects. It's the hom thingies that are we're waving the magic wand over that are turning sets to objects here. So we have a class of objects. So for any objects, we get hom xy. Maybe to be very precise, I'll say in A, instead of doing that here. Category A, enriched over C. I'm just copying that notation because we had it on the board back there. You don't always need to say what category you're in, but do that. So what is this thing? What type of entity is this thing?
The object in C,
Which is a
finite groupoid.
which is a groupoid, yeah, so a finite groupoid. And then we need to talk about composition. So for composition, you need to think about three objects, x, y, and z.
Imagine the product in this is a product of two bytes.
Right, so we need to try to write down what composition should be like, and it should be going to from Tom xy times Tom yz to Tom xz. And we need to figure out what the heck that means. So all these Toms are groupoids. So this product here had better be some kind of product of groupoids. Well, there's a standard product, Cartesian product of groupoids, where an object in the Cartesian product is a pair of objects, and a morphism is a pair of morphisms. Composition is done component-wise.
Is this the same standard product category?
Right, it's the same as the product of categories restricted to the special case of groupoids. So we get this composition map. If I wanted to be very fancy, I could medium that should know it is composition. So so the key things you have to realize are right. You have to know what you're doing here. This is the product of groupoids. So that's why whenever you're enriching over any category C, you need to know what you need to have some kind of notion of a product for C, general tensor product of some sort. We'll do. Here it's the Cartesian product. And what type of entity is this arrow here?
It has to be a groupoid.
It's a morphism in C, which is, you might have thought it's a functor or something, but no, apparently it's going to be an equivalence class of spans. So that's what it is. This is a span, or really equivalence class. So this, I hope, partially answers your question. A bunch of you asked, where do the morphisms in C show up in this game? They show up here. That's a morphism in C. And so you have to solve what morphisms in C are to get that part. I just want to say a little bit more about this. So just to sort of formally most of the definition. In addition to composition, the category has identities. So, for any object X, you have an identity in Tom XX. Maybe I won't be as ultra formal as possible, but so I should maybe tell you the general theory of enriched categories, but I think we're just going to wing it right now. So I'm saying, so let's just think about this example. The identity is in here. So what does that actually mean to say it's in there? What kind of a thing is this identity?
Like the initial object?
So it's called level.
Object and groupoid.
Like doing tons of things are completely disoriented. So what is this thing here? What type of entity is this thing? It says one groupoid, a finite groupoid. So if I see something is in a finite groupoid, what do I probably mean?
Oh, I said, isomorphism class.
I mean, it's an object. So you say, if you have a category and you write X is in the category, you always mean an object in the category. A specific object.
Well, wait a minute. Didn't you write it in an arrow way, so we could?
Did I screw up? I mean, it did screw up because of this one.
Yeah, I think.
Okay, you're right. I was trying to avoid that. This is like a such a little diagram.
No, I think you have to.
Yeah. I was trying to cut corners. I mean, you should already be suspicious of this notation, right? Because in general, when you're doing enrichment, this is just an object in C, right?
Oh, but this C is a constant.
Normally, you don't know that it's like a set or anything, so it's sort of weird, right? Something to remember. I was trying to sneak around that and
So
say,
it's
well, come on, you know what a member of a groupoid is. But the real correct way to do it is that there's a, oh man, they're going to get even more confused now. Hold on.
It is confusing.
Yeah, well, okay, it's bite the bullet. So when you do this enrichment kind of idea, you really can't talk about members of your Hom thingies, because your Hom thingies might not even be sets. So what you always have to do is replace the concept of a member by a morphism from the unit object, the unit for your tensor product. In this particular case, I'll just take you out of your misery a little bit. This is going to be the terminal groupoid. That is the groupoid that just has one object and one morphism.
Isn't it always the terminal object of your monoidal category?
Now, if you have a category with Cartesian products, the unit for the product is the terminal object, always. But you can have other kinds of monoidal categories with other kinds of tensor products where the unit for the tensor product isn't the terminal object.
Think of the most familiar example of vector spaces, where a tensor product, the vector space is the unit object, is not the terminal.
Yeah, so in Vect has a tensor product. The unit for the tensor product is the one-dimensional vector space, C. But that's not a terminal vector space. The terminal vector space is the zero-dimensional vector space. So it's the one object, one morphism. Boring in a certain sense. But what is this kind of arrow here? What is the ontological status of this arrow?
It's a class of span.
It's an equivalent class of span. So I was wrong. I've been somehow subconsciously thinking it was just a functor. And if you had a functor from the terminal groupoid into some other groupoid, that would just pick out an object. But in fact, it's something a little fancier than equivalent span. I shouldn't have talked about that anyways. I should have flipped over this one. But anyway, that's what it's got to be. And then finally, just to round up the definition, we need associativity to hold. And the left and right unit laws for composition. So the usual category axioms for substitutivity of composition and units work the way they're supposed to, you can write them out in terms of diagrams involving arrows, and that's how you create the concept of enriched category. Okay, well, this is kind of a little scary, but let's do an example of a category enriched over C, and then let's do this process to turn it into a category enriched over finite-dimensional vector space. So here's the key example for us right now. So pick a finite group G. There's a category enriched over C that you can attach to it. And for lack of a better name, I'll call it the Hecke category. Hecke of G. So what are the objects going to be, and what are the Hom thingies going to be? Well, so the objects will be finite G sets. I'll call them things like X, Y, etc. And then I want to say what the Hom thingies are. So Hom in here. Maybe I won't write the subscript Hecke G. You're just now supposed to be smart enough to know. No, you shouldn't be smart enough because you're going to be changing. You're doing this categorification process, so it should be very pedantic. So we're going to, I have to tell you a Hom thingy.
That's a piece of capitalism.
Oh. So what type of thingy are we looking for here?
Hopefully not so cheap.
What? Not what?
That's gonna be
Not what
objective.
type of thing
Oh.
there is a thingy.
Oh.
What type of thing?
Finite groupoid.
It better be a finite groupoid dust, not groupoid dust. Right?
Oh.
It's,
Yeah,
so
yeah.
you're suffering classic level shift syndrome, right? So normally when you're doing mathematics, you've got some big set in the background and you're studying a thing in it, and you don't worry about it too much. But now it's more like you've got a thing inside a thing inside a thing inside a thing, and it's very easy to make a slip where you think you're talking about these, but you really should be talking about those or those. Yeah.
No, I meant the Hom sets are finite groupoids, not
The Hom
consists of
thingies.
Thingies.
The Hom groupoids
Yes.
are finite groupoids, yeah. They're not sets, so calling them Hom sets is a little bad. Right? So this has got to be some finite groupoid associated to X and Y and G. And here's what it is. I'll make it up. It's going to be X times Y weakly mod G. So that's a groupoid, where this is the weak quotient, meaning that we start with the set X times Y, stick in these morphisms from one element of X times Y to another, whenever we have a group element that carries one to the other. So I guess I should also say what composition is. Jim actually said that at the end last time. And I should also say, in theory, what the what this units are. I didn't say that, but do that. But before I even mess around with those, let me think more about this. What I've done here, how I've created this groupoid, what it means. What this has to do with Hecke operators. So sort of take a little detour here. We'll call X times Y weakly mod G. This week, Jim and I have been calling it the Hecke groupoid of X and Y from X to Y. And I just want you to see what it's like, understand what it's like. So, one good way to think about what a groupoid is like is to understand what the components of the groupoid are like, the isomorphism classes. Sort of understand them separately. And so let's think about what a component of this groupoid is like. So, somebody know a nice name for a component of this groupoid. So maybe I should just draw you some little picture to help you get going, right? So a typical object in this groupoid is an element of X times Y. A typical morphism is going to be an element of G together with that object X and Y. And we think of that as a morphism from XY to GX, GY. This is what morphism is. What a morphism looks like. All the morphisms are based on one. That's what the morphisms look like. So what is an isomorphism class in here called? It's called an orbit, right? It's an orbit of the action of G on X times Y. So So the components, or isomorphism classes, are orbits in the G set x times y. We have lots of ways of saying that same fact now. Let me say it in a few different ways. One way to say it, which is just purely notational nonsense, is that this is the least interesting. For any G set S, you can form this weak quotient. And then the set of isomorphism classes, or components, I've been denoted by that. Right? So if I have a category, I call it set of isomorphism classes, that with an underline. And what's that equal to? Same thing, orbits. And how do you write that on the G?
That's small.
Yeah. So, right, so that's decategorifying this groupoid, we get this set. Decategorifying the weak quotient, we get this great quotient. So, okay, so the components of our Hecke groupoid form that set. It's just a set of orbits. This is not anything deep, just playing around with notation.
Is that like the zero homology, like the epsilon test on the basis of
It's a basis of the zero homology. Right. Why am I worrying about the components of this groupoid? Because we're about to hit it with this functor D, which turns groupoid into vector space by taking any groupoid and getting the vector space. Its basis is the components of that groupoid, the zero homology. That's right. So, right. So, okay. So you just forced me to admit that if we well, okay, it might not be the best time to admit it, but you sort of forced me to admit it. So that we have this process that turns our groupoid enriched category, our C enriched category, into a vector space enriched category. This is the process we're calling P bar. And so the way that works, right, is it's just bring this process D to the Hom thingy in our Hecke groupoid. I'm saying something very simple, ways to make words, but I prove that I can reason, I guess. So this thing here, what is this? This is turning a groupoid into a vector space, and as you guys notice, that groupoid is called the homology. Of the groupoid. That vector space is the homology of the groupoid. That's the least of my worries right now. It's a large number of letters. That's the problem. So, and like you guys seem to suddenly remember, the homology of a groupoid is just the free vector space on the set of components. Since we're doing finite-dimensional vector spaces, we can just do the K to the set of components, but the set of components, it's just a set of orbits. Okay. So, but the really important thing is not all this notational fiddling around. The really important thing is that what's the big deal about these orbits in x times y? We have a bunch of ways of thinking about orbits in x times y. Someone give me a name, another more sexy name for an orbit in x times y.
Geometric relations between
Yeah,
objects and
and
x.
invariant geometric relation between a figure of type x and a figure of type y. Or maybe sometimes I would call it an atomic relation, atomic invariant relation between something of type x and something of type y. So that's just taking it back to class 3 or something like that, where Jim was explaining that the orbits in a product of G sets are just ways that a figure of one type can relate to a figure of another type, which are invariant under the action of the group. So elements of this of x times y mod G orbits are also called atomic invariant relations between x and y. Atomic means that you can't chop them up into smaller relations.
You also prove the result long time ago saying these are
These give you the basis of intertwining operators between the permutation representations that we get from x and from y. Those operators are called Hecke operators. That's why we're talking about this. It's supposed to be the fundamental theorem. Hecke operators. So these are a basis for the space
G sets, 3 of x and 3 of y.
yeah, so say k, I'll use k to the x and k to the y to define it. So here, these are the permutation representations. This is short for the permutation representation of G on the vector space k to the x, coming from the action of G on x. And this basis, the elements of this basis are called Hecke operators. So when we take this Hecke groupoid and turn it into a vector space, it's not a weird vector space that we've never thought about before. It's just this vector space here. It's a space of intertwining operators from one permutation representation to another. So let me just write that down. Right, so in this category, in this C enriched category here, we had a common thingy that was a groupoid. Now we can turn it into a vector space, and we get the same vector space as the space of intertwining operators from one permutation representation to another. So if I want to say that in a notation written way, so we apply this decategorification process to our groupoid enriched category and turn it into a vector space enriched category. By definition, that's just what happens when we do degroupoidify groupoidification to this Hecke groupoid, and that is just we've got too many ways to write things now, right? It's getting ridiculous, but so we can come on with new things I'm saying compared to how much I'm writing. It's approaching the fractions, approaching zero, so don't think I'm saying a lot of interesting things now. And this is just what we saw a minute ago. Yeah, K to the set of components, or the set of orbits.
And the fifth one.
And we got another one,
On
which is the same thing as hum in the, so here by hum G, I mean hum in the category of representations of G from the permutation representation K to the X to the permutation representation K to the Y. So that's the fundamental theorem of Hecke operators. So now let me state it as a theorem. So what we've done is we've taken this Hecke category of G, turned it into a vector space enriched category, and see that that's nothing new. So here's our fundamental theorem of Hecke operators. So it says G is a finite group and A is any field of characteristic 0. Okay, we can take this groupoid enriched category that we call Hecke of G, turn it into a vector space enriched category. And what do we get? We didn't quite state the theorem this way yet. I said a minute ago, over there, what happens to the hum thingies in here? Like the hum thingies in here are groupoids, and they turn into those vector spaces. So now let's try to state it in a more global manner. So this groupoid enriched category, or more precisely this C enriched category, is going to get turned over into a finite-dimensional vector spaces over K enriched category. Sorry?
finite-dimensional G1.
No,
Actually,
quite.
not quite. Coming from permutation.
Coming from permutation representations. That's right. So we're not, the objects here at G sets, they're turning into permutation representations. They're not turning into all representations, just the permutation representations. So we could call this category, say, finite-dimensional permutation representations. Infirm rep of G. You want to be very bureaucratic, right? So K. So we're going to field K. So that's the category where the objects are the finite-dimensional permutation representations of G, and the morphisms are just the intertwining operators, the varying operators. And so this is encapsulating in it the statement that the Hecke operators are a basis for the intertwining operators here. Okay, now do you have any questions about that? That's all we did so far in class, and well, in some sense, but we did a lot of other interesting. Now there's a lot more one can say about that, and I think I will mainly avoid saying those things, even though they're interesting. But I think I would instead just want to go on and say some things we might do next. Yes, very roughly, some things we might talk about next. Because we were sort of going in different directions and got hijacked by this quest of stating the fundamental theorem of Hecke operators.
Yeah, I mean, FinVect here does take months as well.
Yeah, and they're probably choking on it right now, right? Because there are a lot of things that it proved and so on. Lots of concepts that would become intuitive only after you work some examples. But I'm not going to do those things right now. I just want to sketch where some places where we could go next. There are lots and lots of things we could do next. I just want to point at one that we've already sort of, we're in the process of dealing with. I feel guilty that I never finished talking about Pascal's triangle, for example. And so let me just say a word or two about that. So here's a span of groupoids. These aren't finite groupoids. This is the groupoid of all finite sets and bijections. They aren't finite groupoids, so the theorems that I just stated today don't quite necessarily apply. We were sticking to finite groupoids in some of our theorems because some of our theorems involve summation, working in the background. There are some formulas involving summation, and those might diverge. Those sums might diverge if you have infinite groupoid, a groupoid with infinitely many components. But nonetheless, we can go ahead and think about the ideas for slightly more general cases. So this is an infinite groupoid. It's very interesting. And here's a little span. I'll put the identity here, and over here, I'll put the functor that takes any set and adds in a disjoint base point, which I'll call 1. I'll call the one element set 1. So that's a functor because you can do it not only to sets but also to functions. Based on the right under the bijection. So here's a little span, and so you can try to take this span of groupoids and turn it into an operator, just like we've been doing. Right? We've been doing it. We've been talking about how you could turn spans of finite groupoids into linear operators. So let's actually do that in this one example. Even though this is a funny example because these are infinite. So what remember we do is we take a homology here, homology here, homology here. We go up using this mysterious, well, tricky transfer concept. We go down using a much less sneaky concept. Let me call this map here P.
Last week is good.
That's why I take this example. Yeah, right. So you may have trouble computing what operator you get here in general because you have to look up the Jim's formula for what the transfer was. But what do you think one shriek is going to be?
The identity.
What?
That's a vector space isomorphism, right?
It's 1.
It's certainly not isomorphism, but it better be the identity. The shriek thing should be some kind of functor, a contravariant functor. So this will just be the identity. That's right. So that's why this is not so bad to work out in the last few minutes of the class. So let's see. I said that the homology of the groupoidifying sets was had a famous other name. Right? There's one isomorphism class of sets for each natural numbers. So we're taking the free vector space on the natural numbers to get our H0 there. And that's often called, what do we call the free vector space on the natural numbers in high school? Polynomials, yeah. We call the algebra of polynomials in one variable. So there it is. So I'm just working out what that previous diagram really amounts to. Right, so remember how it works. You have this equivalent isomorphism class of objects. Right, so you have an n-element set. Right, it's isomorphism class. It's going to give you a basis element for the homology, but we call that x to the n. Think of it as a basis element for the polynomials. So that's how it works. So this map here is what? Or just calculating. So that's just the identity. That would be this map here. I need to say what it does. So I need to say what it does to any basis vector, x to the n, and where does it go? X to the n plus 1. Okay. You know, all these sophisticated concepts turn out not to seem so terrible in examples. And so this map here that we're getting, this linear operator that we're getting from our span of groupoids, it's known as what? Multiplication by x. Yeah, that's right. So that's an example of getting an operator from a span of groupoids. And you see that you get, in this particular case, a very simple sort of operator. If you want to suffer a little bit, you could try to turn this span around and work out the operator. Then you have to do the transfer for a non-identity map, which means you have to really think of the formula for transfer. It's something that's like multiplication by x, but backwards. So instead of raising the degree of a polynomial by 1, it should lower it by 1. And what you hope that it would be?
Differentiation.
Differentiation, DDX. So we'll see if Jim wrote down the right formula. Well, he could like weasel out of it. Say, no, there's some notational difference between what I was saying. But under some good set of conventions, if you turn this around, you should in fact get differentiation, DDX.
Is that all plausible, the division by the third degree?
We'll see. We'll calculate it out. Yeah, so Jim's on the hot seat now. So in physics, those are called annihilation and creation operators. So multiplying by x boosts the polynomial degree by 1, which means it's throwing in one extra particle into the pot. Differentiation reduces the number, reduces the degree by 1. And so we're going to wind up working our way towards some kind of categorified version of quantum mechanics where these operators on the polynomial ring we could think of as coming from spans of groupoids. And this is actually something we talked about in previous runs of this seminar. Jeff Morton wrote a nice paper about it. But here's something else we can do. We can look at, and I'm going to do this in less detail, we can consider some other groupoid. Let's call it, I don't know, Q. So this is the groupoid of finite sets equipped with a chosen subset. So I'm not saying what the morphisms are, but the morphisms are the obvious things. The bijections that map the subset of the first guy into the subset of the second guy. So the point is that this is a special case of a flag. Right? These are the kind of, well, this is a bunch of special cases of flags. So we were talking a lot about n choose k. We have lots of variations on n choose k. And our most sophisticated one was the groupoid n choose k. Right? This is the groupoid of n element sets with a chosen k element subset. And so these groupoids here are just the components of this big fat groupoid here. So if you want to make it look more like math, another name for disjointing is coproduct, sometimes written as sum, so that might start reminding you of something. So here it turns out that we have two interesting spans, well, there are even more, but I want to think about two interesting spans from Q to itself. One of them, right, so we considered a simpler example where we just looked at one span, and that span meant throw an extra bean in the pot, right? That's what the span over there meant. Right? Take an element, a set S, you throw in an extra element. Set with one more element. But now we've got things that aren't just finite sets, they're sets with a subset. And we talked about this like you've got your kids and then the kids on the team. And we saw in our analysis of Pascal triangles that there are like two interesting things you can do into that situation. You throw an extra kid on the team, or you can throw in an extra kid who's not in the team. So that you get two different spans this way. So this is
You want the zero under the bracket in the all these square brackets
0.
to call them groupoids.
I always meant the groupoid, yeah. So add an element to the subset. So you have to figure out what spans these are that I'm talking about. But you can do it. And then there's another one. Add an element that's not in the subset. Some other span. Add an element not in the subset. So those are two processes that you can do to a set with a subset. And so these are some spans of groupoids. When we do degroupoidification to it, they'll turn into linear operators, just like in our simpler example. So these give two linear operators.
Not in the subset.
Not in the subset.
One added to the set, not in the subset.
Right, but you can throw it into the set, but don't throw it into the subset.
That would be slightly right.
I'm speeding up because I'm trying to cover an infinite amount of material in a finite amount of time, so keep speeding up. So these give two linear operators. So before, we're just going to completely get very sketchy now. So before, in the simple example, we got one linear operator and we call it multiplication by x. And that's what it turned out to be. So just what do you think that they're going to be called now? Even though I've given you no justification.
It's x and y, and those because that groupoid is ax, y.
Yeah, there's some subtleties there, actually. What we want to think of them as multiplication by x and multiplication by y.
And you want to think of A0 Q as being k or x, y.
Right, but there's a certain subtlety there in the choice of how you label the variables, because
Right, you have to,
yeah.
Otherwise they wouldn't be these exact multiplications.
Yeah, that's right. But what's the point of this? Well, the point of this is that I said, right, that when we were trying to categorify the Pascal triangle, it involved thinking about the operations of multiplication by x, multiplication by y, and those operations commute, and so you can derive Fundamental Theorem. And I said I want to categorify Pascal's triangle. So instead of thinking of these as operators between vector spaces, I want to somehow think of them something more grandiose. The more grandiose thing is spans of groupoids. So spans of groupoids. Groupoidify down to linear operators. But here we're going to have these and the groupoids, which will be the things that correspond to multiplications by x and multiplications by y, then we'll be able to interpret this kind of formula in a categorified way. So we can categorify this. And then I just want to say, even in more sketchy detail, how I want to generalize this in different ways, which I've already mentioned. I just want to tell you what I haven't forgotten. So after we've categorified Pascal's triangle, what do we want to do? We want to q-deform it. So similarly, for the q-deformed version, which means wherever you saw finite sets running around, you want to now do finite-dimensional vector spaces over the field of the characteristic Q. Now, some things get to be trickier there, but we'll see how we do, and we'll try to get ourselves a categorified version of the q-deformed Pascal's triangle. Okay, once you've got that all up and running, what do you want to do next? Well, here we're talking about two variables, x and y. So one thing you might want to do is have more variables. Why restrict yourself to just two variables? So there's a many variable version of it.
Multinomial theorem.
Yeah. There's a multinomial theorem. So there's a many variable version involving multinomial coefficients. And that's not too surprising because we were already talking about multinomial coefficients. And we are seeing that they're very closely related to more interesting types of flags. So the binomial coefficients are related to the gross monomers. You've got space and subspace, like a bunch of kids and kids on the team. But if you have more interesting flags, you could have nested subspaces, sort of like teams within teams, sort of like the Freemasons, like descending level. And so then there are like more different kinds of operators involved, where you could throw in a kid who's in the club, but he's not like in the secret club within the club, and so on. And so you get a multi-variable version of this kind of thing. Then finally, what you want to really do is remember, I said that the algebras that we start getting here, for example, are not just polynomials into variables, but polynomials into non-commuting variables. So already for the q-deformed two-variable version, we get the quantum plane where x and y don't commute. So we actually have to see why those operators don't commute in that case. And so here we'll get some kind of quantum end space as the corresponding algebra of analogous to this. And I said that one reason why all this stuff is interesting is because the ordinary plane has GL2 acting as symmetries, but the quantum plane doesn't really have a good group acting as symmetries. It has a Hopf algebra acting as symmetries, otherwise known as a quantum group. And so what we'd like to do is to take that quantum group and categorify it too. And it turns out that we don't know quite how to do all of that. We can only sort of categorify part of it so far. So we can try anyway to categorify the quantum group, and not just for the two-variable case, but the n-variable case. So there's a quantum group GLN sub q. If you don't emphasize, well, the field is in here.